Volcanic hotspots spread across the planet. These volcanic activities are far away from Earth's plate boundaries. Their chemical composition is also different from other volcanoes. Now, let's try to know more about volcanic hotspots and mantle plume theory. Mantle plume originate around 2,900 km below our feet. Core-Mantle boundary separates the lower mantle and the outer core. Large amount of heat produced in this layer causing heating of the rocks and rising of mantle plume. Mantle plume takes a mushroom shape because hot material inside the plume rise faster than the plume itself in its surroundings. Most of the plumes cools down and doesn't reach the Earth's surface. Large plumes rises and hit the lithosphere. Here, lithosphere act as a barrier. This will help mantle plume to spread to a larger area. And finally, mantle plume will look like a disc with a tail. Mantle plumes provide a continuous supply of abnormally hot magma to a fixed location. Abnormally high heat facilitates the melting of rocks at the base of lithosphere. This melted rock pushes through the cracks in the crust to form hotspot volcanoes. This process results in large-scale flood basaltic volcanism. This will continuously erupt for a long period. In the later period, large-scale volcanism stops because of the cooling of plume head. But a narrow tail of plume will continuously transport magma to the surface. Hotspot volcanism is responsible for the formation of flood basalt provinces. This map shows Hawaii hotspot. This archipelago is made of 132 islands, and the seamount chain stretching over 1,500 miles from the island of Hawaii in the southeast to the Kure Atoll in the northwest. What is the reason for this formation? We know that each plume is anchored at core-mantle boundary. But here you can see hotspot is changing its position above the surface. It's not because the hotspot is moving, but because the plate is moving. When plate move across the hotspot, it creates a chain of volcanic structures. Yellowstone hotspot situated in United States. Yellowstone hotspot move eastward because the North American plate is moving westward. Position of Yellowstone hotspot can be connected with reservoir basalt groups. Other volcanic structures related with Yellowstone hotspot clearly shown in the map. Now let's try to know more about Louisville Ridge. The Louisville Ridge is also known as Louisville Seamount Chain, is an underwater chain of over 70 seamounts in South Pacific Ocean. Louisville hotspot can be linked with Ontong Javu Plateau. Other nearby igneous provinces also shown here. Island hotspot is responsible for the formation of North Atlantic igneous province. Now let's come back to our Hawaiian hotspot. In the case of Hawaii hotspot, it cannot be related with an igneous province because the Pacific plate is subducting under the Eurasian plate. This subduction zone destroyed the evidence of existence of igneous provinces related with Hawaii hotspot. Siberian traps cannot be connected with Hawaii hotspot because in the last 500 million years, Eurasian plate was never above Hawaii hotspot. Now let's come back to India. In the case of Reunion hotspot in the coast of Madagascar, it's responsible for the formation of Deccan traps. 66 million years ago, when Indian plate on its way to current position crossed over Reunion hotspot, which resulted in the formation of Deccan traps. But not every large igneous province can be explained through plume model. One such exemption is CAMP, Central Atlantic Magmatic Province. Large igneous provinces have geological importance as well as biological interest. If you plot the formation of large igneous provinces graphically, you can see a striking correlation between three factors: formation of large igneous provinces, boundary of geological time periods, and mass extinctions. The boundary of geological time periods can be related with catastrophic mass extinctions. Formation of Deccan Trap coincide with KT boundary that marks the extinction of dinosaurs. The formation of CAMP, Central Atlantic Magmatic Province, overlaps with TJ boundary, that is known for Triassic-Jurassic extinction event. The formation of Siberian Trap coincide with PNT boundary, that mark the end Permian extinctions. At the end of the Devonian period also, Earth experienced large-scale volcanisms. The formation of Willow Trap seems to overlap with Kelsver event, the first and the most important event in the late Devonian extinction. The conclusion is 4 out of 5 largest mass extinctions can be related with large-scale volcanic events. After the discovery of Chicxulub crater made us to conclude that asteroid wiped out the dinosaurs. It led us to believe that asteroid impact was the main reason for mass extinctions. But later researchers emphasized the importance of large-scale volcanism and its effect on the environmental changes and mass extinction events. Of course, asteroids certainly had an important role in biological and geographical changes. But we have to consider the contributions of large-scale volcanisms also. For example, in the case of extinction of dinosaurs, large-scale volcanism has played at least a role through the formation of Deccan traps that started erupting about 400,000 years before the Chicxulub impact and continued for another 600,000 years. This must have put some significant stress on our ecosystem. This topic is still under debate.